So the magnetic field here is going to the right. I'm not going to show you the bar magnets that created this magnetic field. I'm just showing you there's a magnetic field going to the right. And let's say that there was a wire and the current in the wire was going up. So the red lines are the magnetic field lines. And remember, the symbol for magnetic field strength is B. And the I, of course, is the current. Number of coulombs per second, number of amperes. And the question is, and please don't shout out the answer. Let everyone have time, to try to manipulate their right hand to figure out. The question is, what is the direction of the magnetic force on the wire? And there's always 6 answers. Up to the top of the page, down to the bottom of the page, to the right of the page, left side of the page, into the page, or out of the page. And Dorothy, what do you think on this one? Up, down, left, right, into page, out of page. Or do you want to work through it with me? Okay, what do I have to do with my fingers? To my thumb, and what am I going to put my fingers with over here? Yeah, so they're going to go like this, yes. And then I have to put my thumb, which way? Up, because it has to go with the current. Yes, it's going to come out of the palm of my hand. You have to say that sound too, and go like this. So it's going to go out of the palm of your hand. I remember playing some game as a kid where somebody would slap your hand and squeeze, and you had to make a fist, and then they would rub your knuckles or something, and then somehow or another they got the blood out of your hand. Okay? And then when they released it and opened your hand, they would go like this and pull upward. And it was the weirdest thing because as they did that, the blood rushed back into your hand, and it really felt as if something was pulled upward. No one ever did that as a kid? No. Okay. Anyway, so the force would be into the page or into the board. Let's look at another example. This time, all right, you guys okay? This time, magnetic field due to the bar magnets is into the page. And let's say the current in the wire is going down. Well, the thing is, the magnetic field around the wire is going to interact with the magnetic field due to the bar magnets shown in red. And ultimately, the wire experiences a force. And the question is, which way would the force be? Paulie?
To the right.
Fingers go to magnetic field. thumb with the current, force,
To the right.
to the right. Okay. Questions, comments? Now, we talked about how to find the direction of this force, but now we're going to talk about how to find the strength of this force. That's right, ladies and gentlemen. We're going to learn the formula for calculating the force on a current-carrying conductor in a magnetic field. Yes? So this force turns out to be equal to I, the current in the wire. If you have more current in the wire, that wire is going to have a stronger magnetic field, and it's going to feel a bigger force. The next factor, L, where L is the length of the wire that's in the magnetic field. The length of the wire that's in the magnetic field. I times L times V. V is the strength of the bar magnets that you're using, or the strength of the external magnetic field shown in red here. And there's one more term we haven't talked about, and that is the direction between things. Theta is the angle between the current direction and the external magnetic field lines. And what has theta been in every single problem we've done so far? It's been 90 degrees. And what's the sine of 90? 1. So usually theta is 90 and the sine of 90 is 1, and that whole thing just drops off. The sine theta term drops off. But on occasion, it's a factor. So theta is the angle between current direction and external magnetic field. Directions. Sorry for writing sideways. Theta is the angle between the current direction and the magnetic field line's direction. So, like in this problem here, the magnetic field line is going into the page, and the current is going down, and the angle between into the page and down is a 90-degree angle. You get the biggest force when there's a 90-degree angle between the red field lines and the direction of the current. Watch what happens here, though. Let's say you have external magnetic field lines going this way, and you have a wire with electricity. Going that way. If you try to do the right hand rule, and you put your hand flat, and you keep your thumb at a right angle with your fingers, it doesn't work out. Because look, you put your fingers with the red lines, and then you try to put your thumb with the current, and you have to cheat and go like that. But then, but the bottom line, it doesn't work. And what's theta going to be in this case? Yeah, theta in this case would be 0, So when you work out the formula, F equals ILV sine theta, the sine of 0 is 0, so Mike, what does the force come out to be? 0. There is no magnetic force. Okay? Now, you might think, oh, this is kind of cute. Look, the wire has a little force acting on it. No big deal. Well, I'm very excited to show you a use of this magnetic force on a wire. Sometimes this whole lesson is called the motor principle, because this is how an electric motor works. You plug in the electric motor, and the electricity somehow gets something to spin. Every time I turn on the ceiling fan in my family room, as I watch that fan turn, and I think about, oh, I have to put the electricity on, I think about, oh my God, that thing is just harnessing the magnetic force by making the fan turn. So here we have an electric motor. Again, I'm going to attempt to draw a three-dimensional or 3D drawing. I bet you someday, I'll be drawing and you guys will put your 3D glasses on.
We'll be sitting at home in our underwear.
There you go. There you go. More information than I needed to know there.
Underwear.
All right. So, two anchored down bar magnets, of course, if they were free to move, they would go clink, they would attract, but they're anchored down, they can't move. And then in between these bar magnets, what I'm going to attempt to put is say this is like a wire right here. I'm going to attempt to put a loop of wire in like this, right in like this way. I'm going to try to put a loop of wire in between these two bar magnets. So I had like this loop of wire in between the bar magnets. And I'm going to send the current, and this next little piece down here, you might want to hold off on drawing this down here. Down here, in this area here, I'm going to draw some stuff and then I'll come back. But right over here, let's just say that this is the positive, and this here is connected to the negative. So basically you get a current, and the current is going to go up the wire this way, and then it's going to go up this side, and then across the top, and then down across the bottom like that. And if you have a current in a magnetic field, what is that current going to experience? Theo? Anytime you have a current in a magnetic field, a current carrying conductor in a magnetic field experiences a force. And after the 2 o'clock stretch, we'll take a look at the force on each side of this loop. Yeah, baby. Okay, we're back. Ladies and gentlemen, we have a current-carrying loop of wire in between 2 bar magnets. Now, we know that in between the 2 bar magnets, there's an invisible magnetic field going to the right, like this. But I'm just going to erase those because I don't want to get it all crazy in there, making room. But keep that in mind. You have that magnetic field going to the right. Now, if you have that magnetic field going to the right, the current in this wire right here, again, it's a 3-dimensional drawing, so see if you can follow me on this. That wire is supposed to be into the page. So, if that current is into the page, and the field lines are going north to south, and the current is into the page, guess what the direction of the force is going to be on that side of the loop? Down. That side is going to experience a downward force. Meanwhile, if you look at the other side of the loop, the current is coming out of the page, but the field lines are still going north to south. And with the field lines going north to south, which way is the magnetic force going to be on that side? Up. And it's going to end up turning. Okay? So what you have to do now is tape this wire or somehow connect it on an axle in the middle. So somehow, what I'm going to draw right now is not part of the circuit here. It's just some kind of external attachment. Some kind of axis that the circuit is going to be attached to, yes? That's a great question. That's what I need to address. Excellent insight. Okay? The way it is right now, it would only turn 90 degrees, and the loop would go like this. And as a matter of fact, it might have a little momentum. It might go a little farther, but then it would be pulled back to the vertical stance. Yes? Now, if you wanted to keep it going, and then have it keep going, watch carefully. You see how the current on that left-hand side is coming out of the page? Well, as soon as it flips past the vertical, this side over here, where the current is coming out towards me, as soon as it flips past the vertical, if you wanted to keep it rotating, what would you want the current over here to be doing now? Pardon? Sort of. What would we want the current to be doing now over here? Go in. Because now if the current's going in over here, it will keep it torquing. It'll keep it turning. So basically, it'll only turn 90 degrees, but if you want to keep it turning, there's 2 things to do. After it flips over here, look, guys, watch this. You see where my thumb is? What's the direction of the force where my thumb is right now? Up. Now, as soon as it goes past the vertical, the force on my thumb is still going to be up. You know, look, my thumb is this part of the wire right here, yes? So as soon as it flips, my thumb, that's that loop right there, the current's still coming out. What's the direction of the force still? Up. So there's two things to do. One, switch the polarity of the bar magnets. That would make the force go down. Or, more easily done, change the current direction. And if the current direction of my thumb now goes from out to in, we know the in part gets the downward force. So you have to change the current direction every half turn. To do that, we need this device. It's called a split ring commutator. Imagine a cylinder. You know, imagine like this piece right here. See this right here? And imagine there's a slit, like let's say I took a saw and I cut it right down the half. So there's a little slice missing in between the two halves, yes? And then I solder this wire to this piece, and I solder this wire to this piece. And then I take my battery and I bring it up over here, the wires. But then, imagine a paintbrush whose bristles are made out of steel. It's like a paintbrush that has like its little painting brush mechanism is little strands, fibers of steel. So it's like a little steel brush. So I connect the wire to like a little paintbrush with steel fibers that brush up against that barrel. And then over here, I have the little bristles so see if you can follow me on this. Okay? At first, of course, this is always going to stay positive. This is always going to be negative. The current is always going to come up this side, and it's always going to come down that side. When the current goes through here and goes through the brush right here, that brush is touching up against the split ring commutator, piece of metal there. So the positive charge flows up this side, up over here, down around, through here, through there, back through the split ring commutator, through the other paintbrushy thing, and then through the wire. But as the current goes through that loop, what does the loop experience? A force. And when it experiences a force, what does it do? It flips. But when it flips, the split ring commutator flips with it. So, you see this side over here where the pen is located? Right now, it's touching over here, which is connected to the negative. But once it flips past the vertical, this side of the split ring commutator is no longer going to be touching the negative wire. Where is it going to be touching after it flips 90 degrees? The positive side over here. And by doing so, the direction of the current in the wire changes every 90 degrees. So it goes like this. Loop experiences force and rotates. 90 degrees. At that point, due to the split ring commutator, the current direction changes. And then the whole thing starts over again. So it's kind of like 1, 2, and then 3. Well, back to 1. So that loop just will keep on spinning around and around. And then what you could do you could come over here and you can attach a fan blade, and as that magnetic force keeps flipping the loop, guess what it's going to do? Flip the fan. So anytime you're using an electric fan, you're harnessing this magnetic force right there. You know, it all started with, those people in Turkey hanging up a barman, a lodestone, and it comes to this. Look, human ingenuity. Is this amazing or what? Or maybe you're not going to use an electric fan. Maybe you're going to use, whoa, too much there. Maybe you're going to use, electric egg beater in the kitchen. What spins that thing? The magnetic force. Right now, I hear there's a fan up with that projector, keeping the light bulb cool so it doesn't burn out. What's powering that little fan? That magnetic force right there. It's how all electric motors work. My son likes his little electric remote control car. What ultimately makes the tire turn? I know you have to put the battery, but how do they turn the electricity into making something turn, like the tires? Right there, the electric motor. All right, all together, I want you guys to say, "Oh man!
Oh man!
Isn't that amazing?
Come on!
It's just, so cool. Every single time, I take out my electric screwdriver. And basically, what's making my electric screwdriver turn? I got that little, what's making that little head of the screwdriver turn? The magnetic force. Where's the enthusiasm, people?
I already gave all my food.
All right, good job. Now, if you wanted to have, if you wanted to have a greater magnetic force with more oomph, yes, there's a couple things you could do. Instead of just having one loop, and you don't necessarily have to draw this on your diagram, okay, because it gets kind of messy here. Instead of just having one loop, this loop right here could go up and go around again, and go around again, and go around again, and you could have 50 loops before it comes back down. That would make the 60 times stronger. Or you want to increase how much turning power it has inside that coil. Put a piece of iron. That strengthens the amount of turning power. Now tomorrow what we have to do is see how this same mechanism of electric motor is used to make ammeters and voltmeters. I'm going to give you a little coming attraction. You're not going to need the split ring commutators, because with a meter you don't keep the loop turning over and over again. We should write that name down here. Split ring commutator. Don't have to draw this. We'll be drawing it tomorrow. You got your little loop of wire. You put a current through that wire. The wire starts to turn, yes? But what we're going to do tomorrow is we're going to attach little springs right here. Not part of the circuit. And then we're going to put a big needle up here. Little calibration up here. You put a current through that wire. It tries to turn. It has to fight the springs though, yes? And when it starts to turn, because of that magnetic force, what does the needle do? Goes over. That's how electric meters work. And we're going to have to tweak it into a ammeter and tweak it into a voltmeter. But essentially, this is how ammeters and voltmeters, work. So that's a wrap.